Now let's go back to which is very essential part of chapter 21 and chapter 22, which is the situation of two sources, right, in two dimensions, one source here, one source here. We explained this last class, but it's worth going back to that again. And each source is, of course, going to produce a wave pattern there, circular, expanding as time goes on. And suppose that you are interested in finding the point along this line at which you have maximum or constructive interference. So you have maxima. If this is a sound wave, then you're looking for the points where when you move the microphone, you will find the loudest sound. Okay? So suppose that you're standing here at this point. The distance that the wave has traveled, suppose that it's 27 wavelengths. You know, you could count them by the rings, you know, 1, 2, 3, 4, 5. I didn't draw the other ones, but suppose that this is 27. To get here, the wave has to travel a distance of 27 wavelengths. Okay? The wave that is originating at this point is going to have to travel a different distance to get to the same point. So suppose that that distance, if this one was 27, from this plot, you can conclude that that is, if this distance is the same as this distance, right? So that's 27. And you can see here that there is 1 and 2 extra wavelengths that you had to travel, right? So that means that the difference in path length between that and that wave is 2 wavelengths, correct? 2 wavelength difference means that you have an extra oscillation and an extra oscillation. Each oscillation is 2 pi in a phase. That means that the wave that takes this path arrives here with an extra phase of 4 pi, 2 pi and 2 pi, right? With respect to the phase of the wave that took this route, right? So the difference in phase at this point is 4 pi, because any difference in phase multiple of 2 pi means that the two waves are in phase. They're doing exactly the same thing when they arrive at this point, right? If I've drawn all of this, you will have a crest right here, a crest of that source, and you have a crest due to that source right there also. They will be overlapping at that point. Okay, so constructive interference, a point that is going to be loud if this is sound. So what's the difference in path for the two waves? If you do a little bit of geometry and assuming that this is kind of far away with respect to the distance between the sources, then you can see that that distance and that distance up to here are going to be the same. This is going to be, if you draw a line from here to here, it's going to be approximately a right angle there. And therefore, you have a right angle triangle here with the hypotenuse being d, the distance between the two sources. So from that, you get that this side of the triangle, which is d sine theta, theta is the angle. We're going to measure the angle theta from the horizontal, or the line that goes through the middle, right? You can say the line that goes to the central maximum of this pattern. That angle from there to a line that goes to a place where you are looking at this expression. You're standing here, so that defines this angle theta, right? You put your microphone here, okay, that is your angle theta. You draw a line all the way to the middle of the sources. You measure from this horizontal line, that's your theta. And that theta, if you look at this construction, ends up being this same theta over here. So this difference is d sine theta, which is, for this particular example, I chose it to be 2 lambda. But it can be anything, depends on where you are along this line. So that difference, if that difference in path length is d sine theta, then that translates into a difference in phase between the two waves of k times delta r. Delta r is the difference in path length. So k is the wavelength, 2 pi divided by lambda times d sine theta. This is general for any point that you choose on that line. Now if you say, I'm standing at a point where there is a maximum, then that puts some restrictions on this equation. Because if you're at a maximum, the difference in phase is going to have to be a multiple of 2 pi, right? So you're going to do 2 pi, that's missing here, 2 pi over lambda times d sine theta, which is the difference in phase, should be equal to 2 pi times an integer, right? The difference in phase has to be a multiple of 2 pi. So just cancel 2 pi and you end up with this the equation that we showed you before, last class. That the sine of the different angles at which you will find a maxima, the sine of those different angles given m, it's an integer, it's equal to m times lambda divided by d, right? Where m can be 0, and that would describe this line, this maximum. M can be 1, and that would be the next maximum. M equal 2, the next one, and so on. So I want to emphasize that this, what we just said, it's general for any kind of wave, any kind of interference problem where you have two waves that are overlapping at some point. And those two waves are coming from different sources. And also in this equation, we have assumed that the sources were identical, that they are in phase, that those two sources are pulsing at the same time, synchronized. Right? If those conditions are true, then this equation is it's correct if you're far away from the sources, right? And then an additional approximation that you can take, and we'll discuss it when we focus on light, will be the small angle approximation, which is if this is much smaller than this, then for a number of m's, this quantity is going to be small, which means that the sine of the angle is going to be close to being the angle. So you can get rid of the sign here when that approximation is valid.